gravity shapes everything that moves, gathers, or rests in the universe. It is the reason objects fall, planets orbit, stars ignite, and time itself flows at different rates in different places. From the smallest grain of dust to the largest clusters of galaxies, gravity is always present, quietly determining how matter and energy arrange themselves. Welcome to AstraFlow. Here, science drifts quietly and understanding comes without effort. If you'd like, you can share a thought or observation in the comments as you listen. Now let's begin. Gravity is often described as a force, but before definitions, it helps to notice its consistency. Wherever there is mass or energy, gravity is there as well. It does not switch on or off. It does not need contact, intention, or direction. It simply exists as a relationship between things that have mass, shaping how they move through space and time. This constancy is what allows gravity to feel familiar, even when we rarely stop to examine it directly. On Earth, gravity is steady enough that we usually forget about it. You can sit, stand, or lie down without thinking about why your body stays in place. Objects rest on surfaces. Air remains close to the ground. Oceans stay gathered rather than drifting away. These everyday conditions are not neutral defaults. They are the result of Earth's mass interacting with everything nearby. Gravity is working continuously, but without drama, holding systems together so reliably that it fades into the background of awareness. When we speak about gravity shaping everything, we are not describing an active sculptor or a guiding hand. Gravity does not plan or adjust. It follows simple, unchanging rules. Mass attracts mass. The strength of that attraction depends on how much mass is involved and how far apart the objects are. From this simplicity, complexity emerges. Entire planetary systems, star-filled galaxies, and vast cosmic structures arise without any need for instruction beyond these basic relationships. It is useful to slow down and remain with this idea for a moment. Gravity does not rush. It does not act suddenly, except where enormous mass is involved. Most of its work happens gradually, over long periods of time. Mountains form because gravity pulls rock downward, while internal forces push upward. Rivers flow because gravity draws water toward lower elevations. Even the shape of Earth itself is influenced by gravity, pressing matter inward until it settles into a nearly spherical form. This slow, steady influence is part of what makes gravity suitable for calm observation. Nothing about gravity requires urgency to understand. Its effects are patient. If you drop an object, it falls at a predictable rate. If you watch the moon, it returns to the same position in the sky night after night. These repetitions are not coincidences. They are expressions of gravity's stability, repeating the same patterns because the underlying conditions remain the same. As we move deeper into this exploration, we will not rush from one scale to another. For now, it is enough to remain close to the basic idea. Gravity is a universal interaction tied to mass and energy. It does not distinguish between objects by size, purpose, or composition. A pebble, a planet, and a star all participate in gravity in the same fundamental way. The differences we observe come from scale, not from different rules. You might notice that gravity is often invisible until it causes motion. We do not see gravity itself. We see its outcomes: falling, orbiting, compression, balance. This can make gravity seem abstract, but it is no more abstract than the ground beneath you or the air around you. It is simply less noticeable because it operates everywhere at once. There is no place where gravity is absent, only places where its effects are weaker or stronger. In this space of listening, it is not necessary to hold on to every detail. The aim is not to memorize definitions or equations. Instead, let gravity remain as a quiet presence in the background of your awareness. As you breathe, Gravity is holding the atmosphere close to the planet. As your body rests, gravity is providing the downward pressure that defines what rest feels like. Nothing needs to be adjusted or corrected. Gravity is already doing its work. Over the course of this journey, we will gradually widen our view. We will look at gravity near Earth, around planets, within stars, and across the universe as a whole. Each layer builds on the same simple foundation introduced here. There is no sudden shift, no hidden complexity waiting to disrupt the calm. Gravity remains consistent, even as the environments it shapes become larger and more distant. For now, let this first understanding settle. Gravity is not something separate from the world you inhabit. It is one of the basic conditions that make structure, motion, and stability possible. It does not demand attention, but it rewards quiet observation. As we continue, we will return to this simplicity again and again, not to repeat it, but to let it support everything that follows. Gravity can be understood most simply as attraction. Any object with mass exerts a pull on any other object with mass. This attraction does not depend on contact, shape, or composition. It exists as soon as mass exists, and it operates across any distance, no matter how large. While this description may sound minimal, it is enough to explain a remarkable range of natural behaviour. At this level, gravity does not prefer one object over another. A small stone attracts the Earth, just as the Earth attracts the stone. The difference lies in scale. Because Earth has so much more mass, its response to the stone's pull is too small to notice. Yet the interaction is still there, balanced and mutual. Gravity always works this way, as a relationship rather than a one-sided action. This mutual attraction is constant. It does not weaken with time or fatigue. Once mass is present, gravity is already active, shaping how objects move relative to one another. If two objects are left alone in empty space, they will slowly drift toward each other, guided only by this attraction. There is no need for a medium, a signal, or a force carrier in the everyday sense. Gravity is built into the structure of the universe itself. One important feature of gravitational attraction is that it is always attractive, never repulsive. Unlike electric forces which can push and pull, gravity only draws things together. This one-sided behaviour has significant consequences. Over long periods, it allows matter to collect rather than disperse. Clouds of gas can slowly condense, dust particles can meet and stick. Large structures can form without external guidance, simply because gravity favours gathering. The strength of this attraction depends on two factors: how much mass is involved and how far apart the objects are. More mass means stronger attraction. Greater distance means weaker attraction. These two variables are enough to describe why gravity feels strong near Earth but weak between distant stars. The rules do not change, only the conditions do. Consider a simple observation. When you drop an object, it accelerates downward toward Earth. This acceleration happens because Earth's mass creates a gravitational attraction that draws the object inward. The object does not need to be heavy for this to occur. A feather and a stone experience the same gravitational pull per unit mass. Differences in air resistance, not gravity itself, are what cause them to fall differently in everyday conditions. This detail is easy to overlook, but it is important for stabilizing our understanding. Gravity does not favor heavy objects, it treats all mass equally. This equality is part of what allows gravity to shape systems predictably. Planets do not drift randomly, moons do not spiral unpredictably. The same attraction applies everywhere, producing motion that can be traced, measured, and anticipated. Over large distances, gravitational attraction becomes subtle rather than dramatic. The pull between stars in a galaxy is weak at any given moment, but it is steady. Over millions of years, this steady influence organizes stars into rotating disks and spiraling arms. No single interaction is strong, but together they create structure. Gravity does not need intensity to be effective. Patience is enough. As you listen, it may help to let go of the idea that gravity must always feel like weight or falling. Attraction can exist without noticeable pressure. Satellites orbit Earth because they are constantly falling toward it, but also constantly moving forward. The attraction is there, but it does not produce the sensation of being pulled straight down. Instead, it produces curved motion, smooth and continuous. At this stage, there is no need to move beyond attraction. Before introducing more abstract descriptions, it is useful to remain with this simple relationship. Mass attracts mass. Distance moderates the strength of that attraction. From these two ideas, nearly all gravitational behavior follows. There is no hidden mechanism waiting to complicate the picture. Complexity will appear later, but it will grow naturally from this foundation. Let this understanding remain uncomplicated. Gravity does not require visualization or metaphor to make sense. It operates whether we imagine it or not. As an attraction that never turns off, it quietly shapes motion at every scale, from the smallest interactions to the largest structures in the universe. Mass is what gives gravity its strength. The more mass an object has, the more strongly it influences the space around it, and the more noticeable its gravitational effects become. This relationship is simple and steady. There is no threshold where gravity suddenly appears. As mass increases, gravitational influence increases smoothly, without interruption. At small scales, mass can be difficult to notice. A single grain of sand has mass, and it exerts gravity, but its influence is so slight that it is overwhelmed by the gravity of nearby objects. On Earth, the planet's mass dominates nearly every interaction. This is why smaller objects seem to fall toward the ground rather than toward each other. Earth's mass shapes the local gravitational environment, setting the conditions for everything that happens near its surface. As mass increases, gravity becomes more apparent. A mountain has more mass than a stone, and its presence slightly alters the gravitational field around it. Sensitive instruments can detect these variations, even though they are far too small to feel directly. This shows that gravity responds continuously to mass, not just to large celestial bodies. Even modest differences in mass subtly reshape gravitational influence. Planets offer a clearer illustration. Earth's mass is sufficient to hold an atmosphere, retain oceans, and keep the Moon in orbit. Mars, with less mass, has weaker gravity. As a result, it struggles to hold on to a thick atmosphere over long periods of time. The difference is not due to location or composition alone, but to mass. Gravity reflects how much matter is present, expressed through attraction. Stars demonstrate this relationship even more strongly. A star's mass determines nearly everything about its behavior: its size, its brightness, its temperature, and how long it will shine. Gravity compresses the material within a star, increasing pressure and temperature in its core. This compression allows nuclear fusion to occur, releasing energy that pushes outward. The star exists in balance because its mass creates gravity strong enough to compress it, but not so strong that collapse happens immediately. This balance between mass and gravity is not static. As stars burn fuel, their internal conditions change, but the underlying rule remains the same. More mass leads to stronger gravity, less mass leads to weaker gravity. The star adjusts continuously, responding to its own changing mass distribution. Gravity does not decide outcomes. It simply responds to mass as it exists at each moment. Even objects that appear solid and unmoving are shaped by this relationship. Earth's nearly spherical shape is a result of gravity pulling matter inward from all directions. If Earth had significantly less mass, it might not be round. If it had more mass, gravity would compress it further, increasing internal pressure. The familiar form of the planet is not accidental. It reflects a specific balance between mass, gravity, and material strength. As we consider mass, it becomes clear that gravity does not operate in isolation. It is always tied to what is present. Remove mass, and gravity disappears. Increase mass, and gravity intensifies. This direct connection makes gravity predictable. It does not vary unpredictably or respond to conditions unrelated to mass and distance. You may notice that this understanding does not require dramatic language. There is no need to imagine gravity as a force reaching outward or pulling inward with intent. It is enough to observe that mass shapes gravitational influence, and gravity responds faithfully to mass wherever it appears. This simplicity allows gravity to remain consistent across vast differences in scale. For now, let this idea settle gently. Mass and gravity are inseparable. Wherever matter exists, gravity follows naturally, shaping structure and motion without haste. As we continue, we will see how distance modifies this relationship, further refining how gravity shapes everything around us. Gravity becomes weaker as distance increases. This change is smooth and predictable, not abrupt. There is no clear boundary where gravity ends. Instead, its influence stretches outward indefinitely, thinning as objects move farther apart. This gradual weakening is one of the reasons gravity can shape large systems without overwhelming them. The relationship between distance and gravitational strength follows a precise pattern. When two objects move farther apart, the gravitational attraction between them decreases rapidly. Doubling the distance does not halve the force, it reduces it much more than that. This sensitivity to distance explains why gravity feels strong near Earth's surface, but becomes subtle only a short distance away. Near Earth, gravity dominates everyday experience. A few kilometers above the surface, objects still fall back unless they are moving fast enough sideways to remain in orbit. Farther still, gravity continues to act, but its grip loosens. At the distance of the Moon, Earth's gravity is weaker, yet still strong enough to keep the Moon bound in a stable orbit. This balance between distance and attraction defines the structure of the Earth-Moon system. Beyond that, Earth's gravitational influence continues, overlapping with the gravity of the Sun and other planets. There is no point where Earth's gravity suddenly stops and the Sun's begins. Instead, these influences blend smoothly. Objects respond to the combined gravitational environment created by multiple masses. Motion emerges from this shared field, not from isolated pulls. This gradual weakening is essential for stability. If gravity did not diminish with distance, matter would collapse into a single point. Structure would be impossible. Instead, distance allows gravity to organize matter into layers: moons around planets, planets around stars, stars within galaxies. Each level exists because gravitational influence weakens enough to allow separation without losing connection. A familiar observation helps ground this idea. When you step away from a magnet, its pull weakens quickly. Gravity behaves similarly, but on a much larger scale and without ever fully disappearing. The difference is that gravity's reach is universal. Even when its effects are too weak to notice, they still contribute to the overall structure of systems. Distance also allows gravity to act over long periods without immediate change. Two distant stars in a galaxy attract each other very weakly, but that attraction is constant. Over millions of years, it shapes their orbits and contributes to the galaxy's overall rotation. Gravity does not need to act quickly to be effective. Its patience allows order to emerge slowly. As we move through this understanding, it becomes clear that distance is not a barrier to gravity, only a modifier. The same interaction operates everywhere, adjusted continuously by separation. This is why gravity can be both gentle and powerful depending on context. Near massive objects, it is strong and shaping. Far away, it is subtle and guiding. Let this idea settle without strain. Gravity does not reach out aggressively across space. It simply exists, diminishing naturally with distance, allowing complexity and balance to form. In the next part, we will return closer to Earth, using its familiar gravity as a stable reference point for further exploration. Earth's gravity provides a steady reference for understanding how gravity behaves in familiar conditions. Near the surface, gravitational acceleration is almost constant, creating a predictable environment where objects fall, rest, and move in reliable ways. This consistency allows everyday life to proceed without constant adjustment or awareness of gravitational variation. When you place an object on a table, it remains there because Earth's gravity pulls it downward, while the table provides an upward support force. These opposing influences balance each other, resulting in rest. Nothing about this balance requires effort or attention. It happens automatically, reflecting how gravity integrates smoothly into physical systems without drawing focus to itself. The sensation of weight comes from this interaction. Weight is not the same as mass. Mass is an inherent property of matter, while weight depends on the strength of the gravitational field an object is in. On Earth, gravity gives objects a certain weight. On the Moon, the same object has the same mass but less weight, because the Moon's gravity is weaker. This distinction helps clarify how gravity operates as an environmental condition rather than a fixed attribute of objects. Earth's gravity also defines what down means. Down is not a universal direction. It is local, pointing toward the centre of the planet. People standing on opposite sides of Earth are both upright, even though their directions of down point toward the same centre from opposite orientations. Gravity shapes this shared reference, without requiring coordination or alignment. Another quiet effect of Earth's gravity is how it organises fluids. Water flows toward lower elevations because gravity pulls it downward. Oceans settle into basins. The atmosphere becomes denser closer to the surface. These behaviours are stable and repeatable. They do not depend on momentary conditions, but on the persistent presence of gravitational attraction. Earth's gravity is not perfectly uniform, but the variations are small. Differences in terrain, density, and rotation cause slight changes in gravitational strength from place to place. These differences are measurable with precise instruments, yet they remain unnoticed in daily experience. This near uniformity contributes to the sense of calm reliability that gravity provides. It is also useful to notice what Earth's gravity does not do. It does not pin objects rigidly in place. It allows movement, lifting, and motion with relatively little energy. You can walk, jump, and throw objects because gravity, while constant, is not overwhelming. This balance supports motion rather than preventing it. As a reference point, Earth helps stabilize our understanding before we move outward again. Its gravity is strong enough to be felt, but gentle enough to be managed easily. This makes it an ideal environment for observing gravitational effects without extremes. For now, let Earth's gravity remain as a quiet background condition. It is present in every moment, shaping posture, movement, and rest without requiring thought. From this stable foundation, we can continue exploring how gravity behaves in other contexts, carrying this familiarity with us as the scale gradually changes. Orbits are one of the clearest expressions of gravity in motion. An orbit is not a state of suspension or balance in the sense of stillness. It is continuous movement shaped by gravitational attraction. Objects in orbit are always falling toward the body they circle, but their forward motion carries them sideways fast enough that they keep missing it. This combination of attraction and motion creates stable paths. A satellite orbiting Earth is drawn inward by gravity, yet it also moves forward through space. The result is a curved trajectory that wraps around the planet. There is no point where gravity stops acting. There is also no moment where the satellite is held up. The orbit exists because both influences remain present at all times. This balance depends on speed and distance. If an object moves too slowly, gravity pulls it inward and it falls. If it moves too quickly, it can escape the gravitational influence entirely. At certain speeds, the object follows a closed path, returning to the same positions repeatedly. These conditions allow orbits to persist for long periods without intervention. The Moon's orbit around Earth provides a calm, familiar example. The Moon is not hovering, it is moving sideways through space while continuously falling toward Earth. Because its speed is well matched to Earth's gravity at that distance, it follows a stable path. Over long timescales, small adjustments occur, but the overall motion remains steady. Planets orbit the Sun in the same way. Each planet's distance and speed determine its orbital shape and period. There is no need for guiding forces or corrections. Once established, orbital motion can continue for billions of years, shaped only by gravity and motion. Orbits are not limited to circles. Many are slightly elongated, forming gentle ellipses. This variation arises naturally from the conditions present when the orbit formed. Gravity accommodates these differences without disruption. The motion remains smooth, repeating, and predictable. It is also important to note that orbits occur at many scales. Electrons orbit atomic nuclei in ways that reflect similar principles, though governed by quantum rules. Stars orbit the centers of galaxies. Galaxies orbit within clusters. At each level, gravity provides the inward pull, while motion supplies the outward tendency. What makes orbits especially calming to observe is their regularity. Once an orbit settles, it does not require effort to maintain. There is no energy cost to continue moving along the same path. This efficiency allows gravitational systems to remain stable over immense spans of time. As you consider orbital motion, there is no need to imagine forceful pulling or tension. Gravity guides motion gently, shaping paths rather than controlling them. The result is a quiet choreography of movement, repeating without urgency. Let this idea rest without conclusion. Orbits show how gravity shapes motion through balance, not restraint. In the next part, we will see how this same attraction and balance allow planets themselves to form from scattered material, continuing the gradual expansion of scale. Planet formation begins with gravity acting on small scattered material. In the early stages of a planetary system, dust and gas move through space without fixed structure. These particles do not need to be directed or organized. Gravity alone is enough to begin the process of gathering, even when the individual pieces are tiny. As particles drift, they pass near one another and experience slight gravitational attraction. At first, this attraction is very weak. Collisions are gentle, often slow enough for particles to stick together rather than break apart. Over time, small clusters form. As these clusters grow, their mass increases, and with it, their gravitational influence. This gradual amplification is steady rather than sudden. Once a growing body reaches a certain size, it begins to dominate its local region. Nearby material is more likely to be drawn toward it than toward smaller neighbours. This does not happen all at once. The process unfolds over millions of years, with material accumulating layer by layer. Gravity does not rush the outcome. It allows structure to emerge at a pace set by mass and distance. As a forming planet grows larger, gravity begins to shape its internal structure. Heavier materials tend to sink toward the centre, while lighter materials remain closer to the surface. This separation happens slowly, driven by gravity pulling denser matter inward. Over long periods, this leads to layered interiors, even before the planet becomes geologically active. The growing planet also clears its orbital path. Smaller debris is either absorbed, pushed into new orbits, or scattered away through gravitational interactions. This process contributes to the distinct spacing of planets within a system. Each planet's gravity establishes a region of influence, reducing competition for material nearby. Throughout this formation process, gravity works without preference. It does not distinguish between rock, ice, or metal. It responds only to mass. The variety of planets that emerge reflects the conditions of the surrounding environment, not changes in gravitational behaviour. Gravity remains consistent, allowing different outcomes from different starting materials. A quiet example of this process can be seen in debris disks around young stars. Observations show rings and gaps forming naturally as gravity shapes the distribution of material. These patterns are not designed. They arise because mass attracts mass, and motion responds accordingly. Planet formation illustrates gravity's patience. There is no single moment when a planet appears. Instead, there is a continuous transition from scattered particles to a coherent body. At no point does gravity change its rules. It simply continues to gather, compress, and organize matter. As this idea settles, it is useful to notice how gravity builds complexity from simplicity. Without instruction or variation, it produces worlds. In the next part, we will look inside these worlds, exploring how gravity continues to shape planets long after they have formed. Once a planet has formed, gravity continues to act within it, shaping its interior over long periods of time. Gravity pulls all of the planet's material toward its centre, creating pressure that increases with depth. This inward pull does not stop after formation. It remains active as long as the planet exists. Because of gravity, planets tend to become round. Material at the surface is pulled inward from all directions, smoothing out large irregularities. Smaller bodies with weaker gravity may retain uneven shapes, but as mass increases, gravity overcomes material strength. The result is a gradual settling into a nearly spherical form. This shape is not imposed. It emerges naturally from gravity acting uniformly toward the centre. Inside a planet, gravity creates pressure gradients. Near the surface, pressure is relatively low. Deeper inside, the weight of the overlying layers increases pressure steadily. This compression affects how materials behave. Rocks may become denser. In some cases, heat builds as pressure increases, contributing to internal activity over geological timescales. Gravity also influences how materials separate within a planet. Denser substances, such as iron, tend to move toward the centre, while lighter materials remain closer to the exterior. This process, known as differentiation, happens gradually. It does not require sudden melting or violent motion. Gravity alone provides the persistent pull needed for heavier elements to settle inward over time. This internal arrangement has long-term consequences. The presence of a dense core can influence a planet's magnetic field, while layered interiors affect how heat moves outward. Gravity does not directly create these features, but it establishes the conditions that make them possible. By organising matter inward, it sets the stage for further physical processes to unfold. Earth offers a stable example. Its core, mantle, and crust reflect gravity's long-term influence on material distribution. These layers did not form quickly. They developed as gravity continued to pull matter inward, allowing denser materials to sink. The planet's internal structure remains dynamic, but the gravitational framework stays constant. Even after billions of years, gravity continues to shape a planet's interior. Mountains slowly relax under their own weight. Deep structures adjust as material flows on timescales far longer than human observation. These changes are subtle and slow, guided by gravity's steady influence rather than sudden force. As you consider a planet from this inward perspective, it becomes clear that gravity does not act only on surfaces or orbits. It permeates the entire body, quietly determining how matter arranges itself from the centre outward. This internal shaping is continuous, without milestones or endpoints. Let this idea settle without resolution. Gravity works inside planets as patiently as it does in space, shaping form and structure through constant inward pull. In the next part, we will move outward again, looking at how gravity operates on a large scale within stars. Stars are shaped by gravity from the moment they begin to form. Like planets, they start from diffuse material, but the scale and conditions are different. Large clouds of gas, mostly hydrogen, drift through space. Within these clouds, small variations in density appear. Where material becomes slightly more concentrated, gravity becomes slightly stronger, and that small difference is enough to begin collapse. As gravity pulls gas inward, the cloud compresses. Compression raises temperature and pressure at the center. This heating is not sudden. It builds gradually as more material falls inward under gravity's influence. The process continues until conditions at the core become extreme enough for nuclear fusion to begin. At that point, a star is born. Once fusion starts, gravity and pressure enter a long-lasting balance. Gravity pulls inward, trying to compress the star further. Fusion releases energy that pushes outward, resisting collapse. The star remains stable because these two influences counteract each other continuously. Neither one wins completely. The star exists in this balanced state for most of its life. A star's mass determines how this balance is maintained. More massive stars experience stronger gravity. To remain stable, they must generate more energy at their cores. This makes them hotter and brighter, but also shortens their lifespans. Less massive stars have weaker gravity, lower core temperatures, and burn their fuel more slowly. The rules do not change. Gravity simply responds to mass. Throughout a star's life, gravity shapes its size and structure. It keeps the star compact rather than diffuse. It ensures that fusion occurs in the core, where pressure and temperature are highest. Without gravity's inward pull, the gas would spread out and fusion would never begin. Gravity does not create energy, but it creates the conditions that allow energy generation to take place. The surface of a star reflects this balance as well. The star does not expand indefinitely because gravity holds it together. It does not collapse immediately because internal pressure pushes outward. The visible size of a star is the result of these opposing influences finding a steady arrangement. Even in calm observation, it is clear that stars are not static objects. Material inside them moves slowly. Energy flows outward. Yet through all this motion, gravity provides containment. It does not adjust itself dynamically. It remains constant, allowing the star to change internally while staying coherent as a whole. As this understanding settles, it becomes easier to see gravity as a sustaining influence rather than a destructive one. In stars, gravity does not simply pull inward. It enables long-term stability by setting the conditions for balance. In the next part, we will observe what happens when this balance changes, and gravity begins to dominate in new ways. When a star's internal balance begins to change, gravity becomes more prominent. This change does not happen suddenly. It unfolds as a consequence of how stars use their fuel over time. As fusion converts lighter elements into heavier ones, the amount of energy produced in the core gradually shifts. Gravity remains constant, but the pressure opposing it can weaken. In smaller stars, this transition is gentle. As fusion slows, gravity causes the star to contract slightly. The outer layers adjust and the star settles into a denser, quieter state. The process is gradual, without sharp boundaries or dramatic motion. Gravity guides the material inward, allowing the star to find a new equilibrium rather than collapsing completely. In larger stars, the situation is different because gravity is stronger from the beginning. When fusion can no longer produce enough outward pressure, gravity pulls the core inward more forcefully. The star responds by compressing its inner regions. This compression can briefly trigger new stages of fusion, each one shorter than the last. Gravity continues to shape the sequence, determining how far the process can go. Eventually, some stars reach a point where fusion can no longer counter gravity at all. At this stage, gravity takes the lead. The core contracts rapidly compared to earlier phases, though still following physical laws rather than sudden collapse. The outcome depends on the remaining mass. Gravity does not choose the result. It responds to what is present. For stars with moderate mass, gravity compresses the core into a white dwarf. In this state, the star becomes small and dense. Gravity is balanced not by fusion, but by the resistance of matter itself. The star no longer produces energy through fusion, yet it remains stable, because gravity and internal pressure reach a new balance. In more massive stars, gravity compresses the core even further, forming a neutron star. Here, matter is packed so tightly that individual particles are pressed into close alignment. Gravity is intense, but it is still balanced by internal forces. The star becomes compact and dense, yet stable over long periods. Throughout these transformations, gravity behaves consistently. It does not suddenly become violent or unpredictable. It follows the same principles as before, responding to mass and distance. The differences we observe arise from scale, not from changes in gravity itself. As you consider these stellar changes, it may help to notice the continuity. Gravity does not mark endings or beginnings. It guides transitions from one stable state to another. Even when conditions become extreme, gravity remains patient, shaping outcomes according to simple rules applied over immense timescales. Let this understanding rest without finality. Gravity's role in stellar change is not about destruction, but about adjustment. In the next part, we will move toward the strongest known expressions of gravity, where mass and curvature reach their limits. Black holes represent the strongest known expressions of gravity, but they emerge from the same rules that apply everywhere else. They are not separate phenomena or exceptions. They form when a large amount of mass becomes concentrated into a very small region of space, causing gravity to dominate more completely than in any other known structure. When a massive star exhausts its ability to resist gravity, its core can continue to contract beyond the neutron star stage. If the remaining mass is great enough, no known internal pressure can halt the inward pull. Gravity compresses matter further, shrinking the core until it occupies an extremely small volume. At this point, a black hole forms. This process follows directly from gravity responding to mass, without new principles or forces. A black hole is defined by a boundary known as the event horizon. This boundary is not a surface in the usual sense. It marks the region where gravity becomes strong enough that nothing moving at or below the speed of light can escape. Outside this boundary, gravity behaves much like it does around any other massive object. Inside it, paths through space curve inward so strongly that all motion leads deeper inside. It is important to notice what a black hole is not. It is not a cosmic vacuum cleaner pulling everything nearby into it. Objects must come very close to be affected strongly. From a distance, a black hole's gravity is no different from that of any other object with the same mass. Planets could orbit a black hole calmly if placed at the right distance. Gravity remains consistent even here. Within the event horizon, gravity shapes motion in a way that no longer allows outward paths. This does not mean sudden destruction at the boundary. Crossing the event horizon would not involve a sharp physical impact. It would feel continuous, governed by the same gravitational influence, becoming gradually stronger as distance decreases. Black holes show how gravity can reshape space itself. Near them, paths that would normally be straight become strongly curved. Time and space respond together, adjusting to the presence of concentrated mass. These effects are extreme, but they are extensions of the same behavior seen near planets and stars, differing only in degree. As stable objects, black holes can persist for extremely long periods. They do not consume energy in the way stars do. Gravity holds them in a steady state, defined by mass, rotation, and charge. Once formed, they become part of the gravitational landscape, influencing surrounding matter through attraction rather than activity. As this idea settles, it becomes clear that black holes are not endpoints in a dramatic sense. They are regions where gravity's shaping role becomes especially clear. They follow the same rules introduced at the beginning, applied under intense conditions. In the next part, we will look at how gravity affects something even more familiar and subtle, the path of light itself. Gravity affects more than just solid objects and gases. It also influences light. This influence is subtle in everyday conditions, but it becomes measurable near large masses. Light does not have mass in the traditional sense, yet it still follows the structure created by gravity. This behaviour reveals that gravity is not only a force acting on objects, but a property of space itself. When light passes near a massive object, its path bends. This bending does not happen because light is being pulled like a physical object. Instead, light follows the curved geometry of space created by mass. The result appears as a gentle deflection, noticeable only when large distances or strong gravitational fields are involved. One of the clearest observations of this effect comes from gravitational lensing. When light from a distant star or galaxy passes near another massive object on its way to us, the light's path curves. This can cause the distant object to appear slightly shifted, stretched, or even multiplied into arcs and rings. These images are not distortions of the object itself, but of the space the light travels through. This bending of light happens continuously and predictably. The amount of bending depends on the mass of the object and how closely the light passes by it. Near Earth, the effect is extremely small. Near stars, it becomes measurable. Near black holes, it becomes pronounced. The rule remains the same at every scale. Gravity also affects the energy of light. As light moves away from a strong gravitational field, it loses energy and shifts toward longer wavelengths. This is known as gravitational redshift. The light is not slowed in the usual sense. Instead, the stretching of time in stronger gravity alters how the light's frequency is measured. This effect has been confirmed through precise experiments and observations. These interactions between gravity and light allow gravity to be studied even where matter is scarce. By observing how light bends and shifts, scientists can infer the presence of mass that cannot be seen directly. Gravity leaves its imprint not through visibility but through influence. Light becomes a quiet messenger, tracing the shape of space without resistance. What is notable is how calmly these effects occur. Light does not scatter or collide. It adjusts its path smoothly, following the contours set by mass. There is no turbulence or disruption. The transition from straight-line travel to curved paths happens gradually, reflecting the continuous nature of gravitational influence. As this understanding settles, gravity begins to feel less like an invisible pull and more like a condition of movement. Objects and light alike respond to the same underlying structure. They follow paths that feel natural within the space they occupy, without effort or awareness. For now, let this idea remain simple. Gravity shapes the routes light takes just as it shapes the motion of matter. In the next part, we'll step further into this perspective, where gravity is no longer described as a force at all, but as the geometry of space and time themselves. At deeper levels of understanding, gravity is no longer described as a force pulling objects toward one another. Instead, it is understood as the curvature of space and time caused by mass and energy. This perspective does not replace earlier descriptions. It extends them, providing a framework that explains why gravity behaves as it does, especially in extreme conditions. Space and time are not separate backgrounds in which events happen. They form a connected structure known as space-time. Mass and energy influence this structure, causing it to curve. Objects and light move along paths within this curved space-time. What we experience as gravitational attraction is the result of following these paths, not the result of a pulling force acting at a distance. A simple way to orient to this idea is to imagine motion without resistance. An object moving freely through space-time follows the straightest possible path available. When space-time is curved by mass, those straight paths bend. The object is not being pulled off course. It is moving naturally within a curved environment. Gravity becomes the expression of geometry rather than force. This understanding explains why gravity affects everything equally. Objects with different masses follow the same paths when placed in the same gravitational conditions. Their motion depends on space-time shape, not on their individual properties. This is why gravity feels universal and impartial. It is built into the structure all objects move through. Near massive objects, space-time curvature becomes more pronounced. Paths that would normally remain separate begin to converge. Time itself flows at different rates depending on position within the gravitational field. These effects are not additions to gravity. They are direct consequences of space-time responding to mass and energy. What is important to notice is how continuous this picture remains. There is no sudden change between weak and strong gravity. As mass increases or distance decreases, curvature increases smoothly. The same principles apply near Earth, near stars and near black holes. The difference lies in degree, not in kind. This geometric view also explains why gravity cannot be shielded or blocked. Space-time curvature is not something that can be turned aside or absorbed. Objects exist within it, and their motion reflects its shape automatically. Gravity does not act through a medium that can be interrupted. It is the medium itself. As this idea settles, it may feel less concrete than earlier descriptions. That is natural. The aim is not to visualize curvature perfectly, but to recognize that gravity is not an external influence imposed on objects. It is part of the environment they move within. Motion follows structure quietly and consistently. For now, let this understanding remain gentle and incomplete. There is no need to hold on to formal definitions. It is enough to sense that gravity shapes space and time together, guiding motion without effort. In the next part, we will observe how this shaping of space-time influences the flow of time itself. Gravity influences the flow of time. This effect is subtle in everyday conditions, but it is real and measurable. Time does not pass at the same rate everywhere. Its flow depends on the strength of the gravitational field present. Where gravity is stronger, time moves more slowly relative to regions where gravity is weaker. This difference is not a matter of perception or sensation. Clocks placed at different heights above Earth's surface tick at slightly different rates. A clock closer to the ground, where gravity is marginally stronger, runs more slowly than one placed higher up. The effect is extremely small, but it has been measured repeatedly and confirmed with precision instruments. The reason for this lies in space-time itself. Gravity curves space-time, and this curvature affects both space and time together. As mass bends space-time, it alters the paths along which time progresses. Time remains continuous, but its pace changes depending on position within the gravitational landscape. This variation becomes more noticeable near very massive objects. Near a star, time runs more slowly than it does far away. Near a black hole, the difference becomes extreme. From a distant perspective, time near the event horizon appears to slow dramatically. For an object experiencing that gravity locally, time continues normally, but its relationship to distant clocks changes. These effects are not theoretical abstractions. They are part of how modern technology operates. Satellite systems that rely on precise timing must account for gravitational time differences to function correctly. Without these adjustments, small discrepancies would accumulate and lead to noticeable errors. Gravity's influence on time is already part of practical everyday systems. What remains consistent is that gravity does not disrupt time. It does not stop it or fracture it. Time continues to flow smoothly everywhere. Gravity simply shapes the rate at which that flow occurs. In the same quiet way it shapes motion and structure. There is no need to imagine time stretching or compressing dramatically as a visual process. It is enough to recognize that gravity establishes a gentle gradient in time's passage. Differences are continuous, not abrupt. There are no boundaries where time suddenly changes behavior. As you listen, you can allow this idea to remain calm and observational. Gravity influences time without drawing attention to itself. The effect exists whether or not it is noticed, woven into the structure of space-time alongside motion and distance. Let this understanding settle without emphasis. Gravity shapes not only where things move, but how moments pass. In the next part, we will step back again, observing how gravity operates across much larger scales, shaping entire galaxies and clusters without urgency. On the largest visible scales, gravity organizes vast collections of stars into galaxies. These structures are not fixed or rigid. They are dynamic systems held together by mutual gravitational attraction. Each star moves within the gravitational environment created by all the others, responding to the combined influence rather than to any single source. Galaxies form where matter becomes slightly denser than its surroundings. Over time, gravity draws additional material inward, strengthening the region's influence. Stars begin to orbit a shared center, forming rotating systems that can persist for billions of years. The shapes of galaxies, spirals, ellipses, and irregular forms reflect how gravity and motion interact over long timescales. Within a galaxy, gravity does not act uniformly. Regions with more mass exert stronger influence. Stars closer to the center typically move faster, responding to the greater gravitational pull there. Farther out, motion slows but remains bound. These variations create the overall structure of the galaxy without requiring central control or coordination. Gravity also governs how galaxies interact with one another. When galaxies pass nearby, their gravitational fields overlap. Stars and gas respond by shifting their orbits gradually. These encounters unfold slowly, often over hundreds of millions of years. Even in these interactions, gravity remains patient, shaping outcomes through steady influence rather than sudden change. Clusters of galaxies represent another level of organization. Here, gravity binds hundreds or thousands of galaxies together. The distances are immense, and the individual attractions are weak, but the combined effect is sufficient to maintain cohesion. Gravity does not need closeness to operate. It works across vast separations, given enough time. These large-scale structures reveal gravity's cumulative nature. A single gravitational interaction may be small, but many interactions together produce stability. Motion within galaxies and clusters remains orderly, not because it is simple, but because gravity's rules apply consistently to every component. As you consider these scales, there is no need to imagine motion speeding up or becoming chaotic. Most movement is slow, measured over spans far longer than human lifetimes. Gravity shapes these systems with the same calm regularity seen near Earth, extended over much greater distances. Let this idea rest quietly. Gravity organizes the largest visible structures in the universe without urgency or direction. In the next part, we will consider how gravity operates alongside the expansion of space itself, adding another layer to this wider view. Gravity operates within a universe that is also expanding. These two behaviors are not in conflict. They coexist, each shaping structure in its own way. Expansion describes how space itself stretches over time. Gravity describes how mass and energy influence that space locally. Together, they define how large-scale structure develops and persists. On the larger scales, distant galaxies move away from one another as space expands between them. This motion is not caused by galaxies travelling through space, but by space itself growing. Gravity does not stop this expansion everywhere. Instead, it counteracts it where mass is concentrated. Within galaxies and clusters, gravity is strong enough to hold matter together despite the overall stretching of space. This balance creates a layered universe. Locally, gravity dominates. Stars remain bound to galaxies. Galaxies remain bound within clusters. On much larger scales, where matter is more evenly distributed, expansion becomes the dominant influence. The same laws apply throughout. The outcome depends on scale and density. not on different rules. It is useful to notice how calmly these processes interact. Expansion does not tear structures apart abruptly. Gravity does not force everything to collapse inward. Each influence acts where it is strongest, allowing both gathering and separation to occur simultaneously in different regions. Over long periods, gravity shapes how matter responds to expansion. Regions with slightly more mass slow the local expansion more than regions with less. This difference allows structure to emerge gradually. Small variations grow into galaxies and clusters because gravity gently resists expansion where mass is present. From this perspective, gravity appears as a stabilizing influence within a changing environment. It does not oppose expansion universally. It creates pockets of coherence within it. These pockets persist for immense spans of time, allowing stars to shine and galaxies to maintain form even as the universe grows larger. There is no need to imagine a struggle between gravity and expansion. They are parts of the same physical description, working together to shape the universe's overall pattern. Expansion sets the broad context. Gravity defines the local detail. As this idea settles, the universe can be seen as both dynamic and stable at once. Space stretches, yet structures remain. Motion continues, yet patterns endure. Gravity plays its role quietly, without interrupting the larger flow. In the next part, we will step back in time, observing how gravity has shaped structure from the early universe to the present, maintaining continuity across vast stretches of history. Gravity has shaped structure consistently across the entire history of the universe. From the earliest moments after expansion began, gravity has been present, responding to even the smallest differences in density. Where matter was slightly more concentrated, gravity was slightly stronger. Over time, these small differences became meaningful. In the early universe, matter was spread out and nearly uniform. Temperatures were high, and structures had not yet formed. Gravity worked quietly within this smoothness, slowly amplifying tiny variations. Regions that were denser attracted more matter, becoming denser still. This process did not require complexity or direction. It followed naturally from gravity responding to mass wherever it appeared. As the universe cooled, gravity continued this patient work. Gas gathered into large clouds. These clouds fragmented into smaller regions, each shaped by its own gravitational influence. Stars began to form. Galaxies emerged. At every stage, gravity acted in the same way it does now, following unchanging principles across changing conditions. What is striking is how little gravity itself has changed. The universe has expanded, cooled, and diversified, yet gravity has remained stable. The same attraction that guided early matter into the first stars now governs the motion of planets and satellites. There has been no transition to a different mode of behaviour. Gravity's consistency allows continuity across time. This continuity makes it possible to trace present-day structures back to their origins. The arrangement of galaxies reflects gravitational interactions accumulated over billions of years. The distribution of stars within galaxies carries the imprint of long-term gravitational balance. Nothing needed to be reset or redesigned as conditions changed. Gravity adapted automatically because it responds only to mass and distance. Even as stars are born and fade, gravity remains. It does not depend on the presence of light or energy production. Long after a star has exhausted its fuel, gravity continues to shape what remains. Remnants orbit, merge, or drift according to the same rules that govern their formation. As you rest with this idea, time becomes less segmented. Gravity does not mark eras. It does not distinguish between early and late. It provides a steady framework within which change unfolds. Events differ, but the underlying structure remains familiar. Let this perspective remain observational. Gravity's role across time is not dramatic. It is quiet and reliable, allowing complexity to emerge gradually. In the next part, we will look at the patterns gravity tends to produce, noticing the recurring forms that appear wherever gravity has time to act. Wherever gravity has time to act, certain patterns tend to appear. These patterns are not imposed from outside. They arise naturally from the way gravity gathers matter and allows it to settle. By noticing these recurring forms, it becomes easier to recognize gravity's quiet influence without needing to focus on individual events. One common pattern is roundness. As gravity pulls material inward from all directions, shapes tend to become spherical. Planets, stars, and many moons share this form, not because it is ideal or efficient, but because gravity smooths out large irregularities over time. Sharp edges and uneven structures slowly relax under their own weight, guided inward toward balance. Another pattern is layering. Gravity sorts material by density. Heavier substances move inward, while lighter materials remain farther out. This happens inside planets, within stars, and even in large clouds of gas. The result is a gradual ordering, with structure emerging through separation rather than mixing. Gravity does not stir matter randomly. It allows it to settle. Disks are another frequent outcome. When material gathers while also moving, gravity shapes it into flattened, rotating forms. Planetary systems, rings, and galaxies often take on disk-like structures. Rotation and gravity work together here, not in opposition. Gravity pulls inward, motion spreads material outward. The result is a stable, thin structure that can persist for long periods. Flows also appear wherever gravity operates. Gas flows inward towards stars. Matter drifts toward the centers of galaxies. Even on Earth, rivers follow paths shaped by gravity, moving from higher to lower regions. These flows are not hurried. They follow gradients set by gravitational influence, adjusting gradually as conditions change. What is notable about these patterns is their simplicity. Gravity does not create intricate designs. It produces forms that are smooth, ordered, and repetitive. Complexity arises when other forces interact with gravity, but the underlying shapes remain familiar. This regularity makes gravitational systems easier to recognize, even across vastly different scales. These patterns do not require constant maintenance. Once established, they tend to persist unless conditions change significantly. Gravity supports stability by allowing matter to find configurations where forces balance naturally. There is no need for correction or intervention. The system adjusts on its own. As this idea settles, it becomes clear that gravity leaves a recognizable signature wherever it operates long enough. Roundness, layers, disks, and flows are not coincidences. They are expressions of gravity working patiently over time. In the next part, we will return closer to our own position, considering how humans observe and measure gravity without placing ourselves at the center of its story. Humans observe gravity from within it. There is no external vantage point where gravity can be seen from the outside. Every measurement, every observation, is made while already participating in the gravitational environment being studied. This does not limit understanding, but it does shape how gravity is approached. Much of what is known about gravity comes from noticing regularities rather than direct sensation. Instruments detect tiny changes in motion, timing, or position. Orbits are tracked, clocks are compared, light paths are measured. Gravity reveals itself through these subtle effects, leaving consistent traces rather than dramatic signals. Importantly, gravity does not place humans in a special position. The same principles that govern falling objects on Earth apply to satellites, planets, and stars. Human-built instruments respond to gravity in the same way natural objects do. There is no adjustment required for scale or significance. Gravity remains indifferent to who or what is observing it. This allows gravity to be described without centering human experience. Observations made on Earth extend outward smoothly to other environments. Measurements near the surface connect naturally to measurements in orbit. Data from distant systems follows the same patterns identified locally. Gravity does not change behaviour based on context. It invites comparison across scales. Technology has expanded the range of gravitational observation without altering its nature. Sensitive detectors measure slight space-time ripples. Telescopes observe how light bends around unseen mass. Satellites monitor timing differences caused by gravitational fields. These tools do not reveal new kinds of gravity. They refine understanding of the same interaction acting everywhere. There is a calm consistency in this. Gravity does not require reinterpretation when conditions change. Whether observed in a laboratory, across a solar system, or between galaxies, it follows the same principles. This continuity allows knowledge to accumulate steadily rather than needing revision at each scale. As this perspective settles, gravity appears less like a subject of study and more like a background condition that can be traced gently through observation. Humans notice gravity not because it calls attention to itself, but because its effects repeat reliably. In the final part, we will let this observation soften, returning from analysis to continuity, allowing gravity to remain present without further examination. Gravity continues whether it is examined or not. It does not respond to attention, interpretation, or understanding. It remains present as a steady condition, shaping motion and structure without interruption. As observation eases, gravity does not recede. It simply returns to the background where it has always been. There is no need to hold the details together now. The attraction, the curvature, the patterns, and the scales do not need to be recalled or organized. Gravity does not require coherence from those within it. It supports continuity on its own, allowing systems to persist even when they are not actively considered. As attention softens, gravity can be noticed in its simplest form. The body rests because it is supported. The air remains close. Objects stay where they are placed. Nothing needs to be adjusted, nothing is moving too fast or too far. The same influence that guides galaxies also allows stillness here. Time continues to pass at its local pace. Motion continues where it is needed and remains absent where it is not. Gravity does not urge anything forward. It allows each moment to arrive and settle naturally, without emphasis or delay. There is no conclusion to reach. Gravity does not resolve into insight or meaning. It remains as a quiet condition, present before observation and unchanged after it. Systems continue, structures remain, and movement follows the same paths it always has. As this exploration comes to rest, nothing needs to be held onto. Gravity remains, steady and unremarkable, shaping everything without calling attention to itself. Everything flows, sleep in that motion.